Hello everyone and welcome to Reinforcement Learning Tutorials. In this tutorial, I will explain you how to implement from scratch the SARSA Temporal Difference Learning algorithm in Python. As you can see over here, I'm using the OpenAI Gym Frozen Lake environment to illustrate and to visualize the performance of the SARSA Temporal Difference Learning algorithm. And consequently, by the end of this video, you will be able to generate this nice simulation over here and to impress your coworkers, your professor, or your colleagues. So, the goal of the Frozen Lake game is to reach the goal field starting from the start field and by avoiding these whole fields. What you can see over here is the learned policy. So the algorithm and the reinforced learning framework is smart enough to find the optimal path that avoids the whole fields. Before I start with the explanations, I would like to mention the following. First of all, it took me a significant amount of time, energy, and planning to create this video, and consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Then, those of you who follow my work or who are my subscribers know by now that I always create a post that nicely summarizes everything that I will explain in this video. This post contains figures, equations, and even Python codes. A link to this post is given in the description below. Okay, so let's start with the explanation. Before watching this video tutorial, it's a very good idea that you become familiar with the basic topics and basic concepts of reinforcement learning. Consequently, I created 3 posts and 3 video tutorials that summarize the basic concepts and topics that you need to understand in order to be able to follow this video tutorial. These topics are installation and getting started with OpenAI Gym and Frozen Lake environment. And to read more about this topic, you can click over here, and here's the post with the YouTube video. Then, you need to get yourself familiar with policy iteration algorithm in Python and tests with Frozen Lake OpenAI Gym environment. And again, you can click over here to find out more information about this important topic. Finally, you need to get yourself familiar with Python implementation of the greedy in the limit with infinite exploration Monte Carlo method. You can read this topic by clicking on this link and reading this post. Here, we will first summarize the SARSA Temporal Difference Learning algorithm. And for that purpose, we will consider the Frozen Lake environment. Basically, the Frozen Lake environment that's illustrated over here consists of 16 fields. The field numbers start from 0 and end at 15. We start our game from the state S or from the field S, and the goal is to reach the goal state or the goal field denoted by G. Besides the start state or the start field S and the goal state or the goal field G, we also have the F fields or the F states. F stands for frozen, and we can safely step on F fields. Besides the F fields, we also have the H fields. The H fields or the H states denote the holes. That is, if we step on the hole, we end the game. That is to say, we fall through the hole and we end the game unsuccessfully. In every state, we can perform 4 actions. We can perform the action down, we can perform the action left, the action right, or the action up. To explain the SARSA Temporal Difference Learning algorithm, we need to introduce the following notation. The current state is denoted by capital S, and over here you can see an illustration. S is the current state. The action taken at the current state is denoted by capital A. Here's the action taken at the current state. The destination state that is reached by taking the action A at the state S is denoted by S prime, and here's the destination state. The action taken in the destination state, S prime, is denoted by A prime. Here is A prime. The reward obtained by reaching the state S prime is denoted by R, and here is R. Then the action value function at the state S and under the action A is denoted by Q, S, A. The action value function is a very important concept, and I explained this concept in my previous tutorial that can be found over here. So you can click over here and read this tutorial to become familiar with this very important topic. Here is the main idea of the SARSA Temporal Difference Learning approach. Before the learning episodes start, we initialize Q, S, A to 0 for all states and A's. That is, we initialize the action value functions to 0. Then we start an episode from the start field S, and we select an action A by using a policy. Policy basically is a rule for selecting the actions in particular states, and I will explain the policy later on. This leads us to the next state, S prime, and we obtain the reward R. So let us illustrate this over here. We start again from the state S. At the state S, we apply the action A. This action A leads us to the destination state, S prime, and we obtain the reward R. Then in the destination state, S prime, we again select an action, and this action is denoted by A prime. Action is again selected by using the policy or by using the optimal control law. Then, having information about S, A, S prime, and A prime, we need to determine an equation for updating the action value functions. And under the assumption that the destination state is not a terminal state, the update equation is given over here. On the other hand, if S prime is the terminal state, then the update equation is given by this equation. This is because in terminal state, we have that Q, S prime, and A prime is identically 0. So to summarize, the SARSA Temporal Difference Learning algorithm updates the action value functions by using these two equations. Let us analyze this equation. Q, S, A is the current value of the action value function in the state S and under the assumption that the action A is chosen. Alpha is a step size, R is the reward obtained by going from S to S prime, gamma is the discount rate, Q, S prime, A prime is the action value function in the destination state S prime under the assumption that the action A prime is taken, and this is the initial value of the action value function. Now it should be perfectly clear why the name of the algorithm is SARSA. This is because to compute the action value function update, we need the current state, S, the current action, A, the current reward, R, next state, S, and next action, A. And that's SARSA or SARSA. Okay, so here's the summary of the SARSA Temporal Difference Reinforcement Learning algorithm. We initialize the state at S. This is our starting state. Then in this state, we apply the action A. And we select this action A by using the epsilon greedy policy that will be explained in the sequel. Then we simulate an episode starting from S, and in every time step of the episode, we recursively perform these three steps. First, we apply the action A and observe the response. This action A will lead us to the destination state S prime. Then, in the destination state S prime, we select the action A prime by using the epsilon greedy policy that will be explained in the sequel. Then, if this destination state is not the terminal state, we update the action value function by using this equation. On the other hand, if S prime is the terminal state, that is, if it is a whole or the goal state, we update the action value function by using this equation over here. After the update is completed, we set S to be S prime and A to be A prime. That is, in the next step, this following situation will occur. Or from the mathematical point of view, we will have the following. So this state over here will become S, and this action over here that we perform will become A. And we perform these steps recursively until we reach the terminal state T. That can be, for example, a goal state or the whole state. And this is one episode. Once we complete this episode, we go back, we reset our environment, and we again start from the state S. In this video, my state S, or the initial state, will always be fixed. However, you can also think of an algorithm that will randomly assign an initial state. Next, we explain the epsilon greedy approach for selecting the actions. So consider the figure given over here. Let us imagine that we are in the state 6. In this state, we can go left, right, down, or up. So these are the actions. So in every state, we have 4 actions. And consequently, in this particular state, we will have 4 action value functions. These action value functions can be represented by this row vector. This value over here is Q6. 6 is the index for state, and the action is 0. 0 action can be, for example, go down. Then, this value over here is the action value function at the state S, and under the assumption, for example, that the action right is being taken. So 1 over here corresponds to the action right. Then this value over here is the action value function at the state S, and better to say at the state 6, and under the assumption that the action up is applied and the index of this action up is, for example, 2. And finally, this value over here is the action value function at the state 6, and under the assumption that the action left is taken and the index of this action is 3. The greedy algorithm selects the action with the column number 1, corresponding to the maximal value of the action value function. That is, since the maximum value is 0.6, we search for an index for which this maximal value is achieved, and the index is 1, since the index here is 0, and the index here is 2, and the index here is 3. Here's the maximum. So we select the action with the index 1. And that's the main idea of the greedy approach. For example, if Q looks like this, we will select the action with the index 0, since the maximum is achieved at that index. This is the main idea of the greedy approach. That is, in every state, we select an action that produces the maximum value of the action value function. However, this greedy approach has one main drawback. Let us illustrate this drawback. Let us suppose that we run the algorithm from the first episode. In the first episode, we randomly select actions since there is no previously computed data on which basis we can estimate Q, S, A. We assume that the initial value of Q, S, A is 0 for all the states and actions. Then, after the first episode is completed, we can obtain an estimate of Q, S, A for the visited states. Now, if we follow the greedy approach, in the second episode, we will always select the actions that are taken in the first episode. This is because in the first episode, only pairs S, A that are visited in the first episode are non-zero, and all other pairs are 0. Due to this, the same set of actions will be selected in all subsequent episodes. Consequently, we might not be able to compute the optimal policy. We might be always stuck, for example, in a terminal hold state. To deal with this problem, we use an epsilon greedy approach. And this epsilon greedy approach is explained in the sequel. Basically, we first select a small number epsilon, and this is a parameter of our algorithm. Then we draw a random number from 0 to 1. Then we check if this number is smaller than epsilon, and if it's smaller, we randomly select an action in certain state S. On the other hand, if this randomly drawn number is larger than epsilon, we select an action that maximizes the action value function in the particular state. That is, we select the greedy actions. So the goal of this relaxation of the greedy approach is to make sure that we explore the environment. That is, sometimes we will deviate from the greedy policy by allowing us to explore other possibilities that might not seem optimal at this point, however, that might lead us to the optimal solution. So, for example, imagine that you're in a known city and that you want to reach the destination, and imagine that you don't have Google Maps. Let's say that you drive, and you somehow reach your destination. And tomorrow morning, you wake up and you memorized how you went to your work by following the path. The question is, will you follow the same path, or will you kind of allow yourself to explore the neighborhood a little bit more and to try to find a more optimal path, that is, a more optimal road, or maybe you can reach your destination in a shorter time interval. So that's the idea of the epsilon greedy approach. That is, we sometimes perform random actions in order to improve our learning policy. However, that's not the whole story. We need to make one additional improvement of the epsilon greedy strategy. Let us say that we performed the experiment for hundreds of episodes. And after this time, we are pretty much confident that our policy is quite optimal. So, do we need to explore anymore? Well, we don't need to explore because we learned the environment sufficiently well. To take into account for that, that is to decrease the number of explorations as the number of episodes increase, we will slowly decrease the epsilon parameter. And in that way, by decreasing the epsilon parameter from one episode to another, we will converge to our optimal policy. So here is the idea. First, during the first episodes, where t can be a relatively small number, let's say 50 or 60, we randomly select the actions in every state. That is, we don't follow the epsilon greedy policy. For example, first 10 trips to my work, I will just randomly try to explore the neighborhood and I will try to find my way. Then, after some time, you gain enough experience. And then from the episode t plus 1, for example, from the episode 101, until some episode and let's say 10,000, we select the actions by using the epsilon greedy approach. Then, after the episode, and that is after 1000 episode, we slowly decrease the epsilon parameter by using this equation. And maybe after 2000 episodes, we will perfectly converge to our optimal policy. Okay, so that was the basic idea of the SARSA temporal difference learning algorithm and the epsilon greedy approach for selecting the actions. Let us now explain how to implement this algorithm in Python. Here is the implementation. I wrote a class called SARSA Learning that implements the algorithm. First, let us focus on this function init. This function takes as an input environment, step size, discount rate, epsilon parameter, and number of episodes. This function accepts these arguments and initializes the corresponding variables of this class. Then, the init function also initializes two variables, that is, a vector called learnPolicy and the matrix called QMatrix. Let us first explain this vector learnPolicy. It is initialized as a zero vector with 16 entries. This is basically the policy that we want to learn. That is, this vector will correspond to the actions that we need to take in certain states. At the end of the day, symbolically, this vector will have 16 entries and every entry will be an action. For example, up, left, right, down, etc. Graphically, this means if this is our frozen lake environment, here I will sketch it. This means if this entry, for example, is 0, in this state, we will perform the action up. If this is the action left, this means that in this state, we will perform the action left, etc. The next variable that we need to explain is this matrix over here. This is our Q matrix, or the matrix representing the action value functions. So this matrix will have 16 rows and 4 columns, and it's, for example, entry given over here, that is entry 0, 0, is the action value function at the state 0 under the action 0. The entry over here, for example, the entry with an index 0, 1, is the action, or better to say the action value function at the state 0 and under the assumption that the action 1 is taken. The function selectAction selects actions by using the epsilon greedy approach. The first argument of this function is the current state. The second argument is the current index of the simulation episode. If the index of the episode is smaller than 100, we randomly select actions. That is, over here, we randomly select a number that can be 0, 1, 2, or 3. On the other hand, if the index of the simulation episode is larger than 100, we use the epsilon greedy approach to select the actions. We first select a random number from 0 to 1. Then we check the index of the simulation episode. If the index is larger than 1000, then we start to slowly decrease epsilon. If the randomly chosen number is smaller than epsilon, then we explore. That is, we return a random action. That is, we select either 0, either 1, 2, or 3. Otherwise, we perform the greedy selection. That is, we return the index of the action that maximizes the action value function. As the name says, the function simulate episodes is used to simulate the episodes. Over here, we loop through the episodes. At the beginning of every episode, we reset the environment. That is, we return the environment to the initial state, meaning that we return the environment or our agent to this state over here. Then in this state, we select an action. For example, we go down. And here we print the simulation index. Here we initialize the terminal state to 0. That is, our terminal state is not reached. Over here, we apply the action A to the environment. This action A will lead us to the state S prime, and we will obtain the index of this state over here. As the response of our environment, we will obtain also R value, and this function env.step will return the value false or true if we reach the terminal state. Then, under the assumption that we are in this state over here, we select an action to compute A prime. We basically provide state S prime and index episode to select action function that then goes into the function and searches for the action by using the epsilon greedy approach. It returns the action prime. That's our A prime. And for example, let us say that this A prime is right. Then having S, R, A, S prime, we can compute, or better to say, we can update the action value functions by using the previously explained iteration. Then, after the iteration is finished, we set S to be equal to S prime and A is equal to A prime, and then we go over here and then we step with the new action A prime over here and we observe the response, and this iteration is iteratively being performed, or better to say recursively, until we reach the terminal state. That is, until this flag over here becomes equal to true. And that's the main idea of the implementation. And finally, after we complete this part over here, that is, after we simulate the algorithm for certain number of episodes, we compute the final policy. And the final policy is computed by using this function. We simply look at the final values of the Q matrix and we select, by using the greedy approach, the best possible actions. Here's the driver code I've wrote that explains how to use this class. First, I import the gym environment. However, you can also import the gymnasium environment and the code will still work in that case. Then I import the numpy, I import time, and I import my class, and the class name is SARSA Learning. Then I create my environment. I specify this parameter is slippery to false since I want to have a deterministic environment. Then I reset my environment. Here you can use these code lines to kind of investigate the environment if you want to play with this. And over here I define the parameters. I define the step size, I define the discount rate, I define the epsilon parameter, and I set the number of episodes to 10,000. Okay, so let us run the code until here and let's see what will happen. Nothing happens as we expected, so let us create an instance of our class. Here I will just call the constructor SARSA Learning. I will specify the parameters and let's see what happens. And here's my SARSA 1. Let's see, is it over there? It is. And let's type whose. Perfect, it's in memory. Then let us simulate the environment. So I will simply call the function simulate episodes and let's see what happens. And here's the learning process. This is the simulation number. We see 10,000 simulations. That's perfect. And let's finally compute the policy. Okay, now the policy is computed. You can basically access this policy by typing something like this. And so let us observe the policy. Okay, cool. So these are the actions that we need to perform in certain states. Perfect. And let us now simulate the learned policy. And let us obtain the animation from the beginning of this video. So I will simply run this while loop to simulate the policy. And let us see the result. And here's our environment. Perfect. It works like a charm. We start over here, then we go down, down, right, right, down, and we reach our destination. Perfect. This works like a charm. Very impressive. Okay, so let us break the simulation. And you can notice over here that you have this annoying window still active. So you can basically close the environment window by executing this command over here. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.